How many elements of group Z50 have order 10? Means number of elements normally we represent by hash symbol. Number, this is for number. The number of elements of order 10 in Z50. This problem can be solved by the formula easily. Number of elements order k in Zn will equal to phi k, where k divides n and 0 if k does not divide n. This is the formula. Directly you can apply Euler phi function. So because 10 divides 50 or 50 is divisible by 10, so number of elements of order 10 can be easily evaluated by this formula, and phi 10 is 4 because 1, 3, 7, 9, these are co-prime with 10, and we have these 4 elements or natural number which are less than 10 and co-prime with. Otherwise you can apply Euler product formula phi 10. This is 10 and product of 1 minus 1 upon pi, where n is p1, p2 and pr, and there it's raised to the power k1, k2 and so on kr. 10 can be easily written as 2 into 5 means power 1 and 1. This is 10 and product of 1 minus 1 upon 2, 1 minus 1 upon 5. This one equal to 10 into 1 upon 2 into 4 upon. For integer k greater than 0, let pk denote the vector space of all real polynomials in one variable of degree less than or equal to k. Define a linear transformation T from P2 to P3 by T of fx, means T sending function x to f double prime x plus x fx. Which one of the following polynomial is not in the range of t? These are some polynomials as a choice to you, and we have to tell about which one polynomial not comes in the range of t. Means t is defined if we are input, then t send input to f double prime, means the double derivative of input plus x, and as a fx means product of x and input. This is the structure of image of t. Now pk, normally pk is a polynomial in one variable of degree at most n, at most k, or if I am using k here, then degree at most k. If I am using n, then degree at most n. We use at most or sometimes less than or equal to k. This is define a linear transformation as given. Then we have to find which options are not in the range of t. Range set of t is all those y is in codomain, and here codomain is P3R, means polynomial, real polynomial of degree at most 3, such that T of f or fx equal to y. This is range set of T. Now find matrix representation of T. Matrix representation T from beta 1 to beta 2. This beta 1 is basis. We normally use basis for, we use for as a term for basis of domain, and beta 2 is basis for codomain. Therefore, beta 1 is 1x x square, as this is domain is P2R, and beta 2 will be 1x x square x cube. This is P3R, means polynomial or real polynomial of degree at most 3. These one, either in beta 1 or beta 2, will help to generate constant term. This x generate linear polynomial. X square will help you to generate quadratic polynomial, and x cube will help to generate cubic polynomial. So these are some basic information either directly or indirectly given to us. This is pre-information. As beta 1 is 1x x square, now find all these images. So consider, let fx is 1, then image R f double prime s, means t sending input as f double prime x x fx. This is the basic formation of image. Then f double prime x will be 0 and x fx will equal to x into 1. This implies f double prime x plus x fx will equal to x, and this x write linear combination of elements of beta 2. This means 0 times 1 plus 1 times x plus 0 times x square plus 0 times x cube. Therefore, matrix representation of T is this 0, 1, 0, 0. This is first column, and it is coming by input 1. Now find all images. As fx is x, this is second element of standard ordered basis for P2R. Then f double prime x will be 0, f double x f x into fx will equal to x into x. This is x square. Write linear in linear combination, means x square can be written as 0 times 1 plus 0 times x plus 1 times x square plus 0 times x cube. So these coefficients are second column 0, 0, 1, 0. Similarly, let fx equal to third element of basis as x square, then f double prime x will be 2, and x into fx will equal to x into x square, means x cube, and this x cube, this implies x f double prime x plus x into fx will be x square. This one equal to x into 2 plus 2 plus x cube. This is 2 plus x cube, and this one can be written as, this 2 plus x cube can be written as 2 times 1 plus 0 times x plus 0 times x square plus 1 time x cube. So third column is 2001. This is 2001, means 4 by 3, because basis B2 means beta 2 is basis for codomain, and this codomain has sorry 4 linearly independent vector. So rows are 4 and domain has 3 linearly independent, so 3 columns. Structure of this is T beta from beta 1 to beta 2, means matrix representation of T. Now come to the option. I am going to write this matrix representation again: 0, 1, 0, 0, 0, 0, 1, 0, 2, 0, 0, 1. This is matrix representation of T and size of 4 by 3. So in range T, what is range T? Linear combination of, if I call this V1, V2, V3, these are vector linear combination of V1, V2 and V3, means any element of range T can be written as linear combination of this or scalar multiple of anyone. So for option A, as option A is x plus x cube plus 2. Now we have to check this is in image or not. Now clearly V1 plus V3, this is V1 and this is V3, is 0, 1, 0, 0 plus 2, 0, 0, 1, means 1, 0, 0, 1. Last constituent into 1. And this vector 2, 1, 0, 1, this is first constituent and it is coefficient of constant term. Constant term. This is coefficient of x, and last is coefficient of x cube, means cubic term. This is coefficient of linear term. Now focus on this. Coefficient of x is 1, and here coefficient of x, this is x and its coefficient is 1, so perfect. Now coefficient of cubic term, this is cubic term and its coefficient is 1 here, and coefficient of constant term, this is constant, so constant term is 2, means all conditions are verified. Similarly we have to check for option B. Now option B is given 2 plus x square plus x cube. Clearly v2 plus v3. v2 is 0 0 1 0 and v3 is 2 0 0 1. As you can check, 2 is coming here. So in matrix representation, 2 is coming in v3 and x cube is also, and x square is coming in v2. So I use v2 v3, and this sum is 2 0 1 1 2 0 1 1. This is coefficient of constant term, this is coefficient of linear term, and this is coefficient of square term or quadratic term, and this is coefficient of cubic term, cubic term. You can check coefficient of constant term is 2, and here coefficient of square term is 1. You can check 1 here, and cubic term is 1. So all conditions are verified. So this is not desired because we are seeking desired, because we are seeking which are not in the range of T or image of T. Now check option C, as option C is x plus 1. So anyhow, this is matrix representation. And we are seeking, anyhow we can write x plus 1 using columns of this matrix representation. But anyhow we can't express x plus 1 as a linear combination of the column of this matrix. So x plus 1 is not in the image of T, means RT. Now similarly you can check for option D. So option D is also not in image of T. This is remark, as matrix representation T beta 1 to beta 2 is of size 4 by 3, means 3 linearly independent column, in image of T, and P2 P3 are, or its dimension is 3 plus 1 is 4 dimensional. So this is contain 4 Li vector, and this is contain 3 Li vector. So it is not on to map. So T is not on to map. If any P and R, the dimension of this set is n plus 1, means 1 degree more, dimension is 1 more at polynomial degree. So this is basic question related to linear transformation, and how we solve it you can check. Let M and R with the real vector space of all n by n matrices with real entries. N is greater than 2. Let A belongs to M and R. Consider the subspace W of M and R spanned by this set. Identity matrix or unit matrix of order n, matrix A square, and integral power of a, then the dimension of W over R is necessarily at most n, infinity, n square, n. Four options is given to us, and which one option is suitable we have to find. As dimension of W over R is asked about, so what is dimension? First important point is, what is dimension? Dimension is number of elements in basis. If it is a basis, then we have two ideas related to basis. Basis can be considered as a smallest spanning set and linearly independent. This is first consideration as we consider, and second is largest linearly independent and spanning set. These two are same when we are dealing with bases, but both conditions are differ in sense. But both conditions are differ in sense. How? It is important how these conditions are differ in sense. So first point is, to justify this condition, consider a vector space RQ. We normally know this is a vector space, and in this vector space, subspaces are plane which is passing through origin, line which is passing through origin, and 0 0 or trivial subspace. Now R3 is generated by this spanning set 1 0 0. This is first element. You can consider 0 1 0. This is second element in a spanning set 2 0 0. This 0 2 0 0 0 1. Clearly, this V1, V2 and V3 are Li vector, are only Li vector. So we can conclude that is cardinality or number of elements in basis. Cardinality of basis is at most number of spanning element, number of spanning elements. Here 4 elements are given, so cardinality of this basis is at most 5, but cardinality of basis in perfect sense is 3, because 3 Li vector and these 3 are spanning set. So it is not important for a spanning set, for a vector space spanning set is unique. This is also a spanning set, and if we put these element in a set, then this one again a spanning set. Now come to the question, how to deal this given problem. So solve this problem, you should take this as a remark. Dimension of Rn is n. Dimension of m by n matrices over R is product of mn. This is remark 1, this is remark 2, or these are points you should know that dimension of M and R, when M and N are same, then this dimension is n square, or you can write n by n in the sense of second. And 4 point is dimension of polynomial of degree at most n in one variable is n plus 1, means 1 exceed. Now clearly, by remark, dimension of M and R, or as this is a vector space, is n square. So dimension of its subspace never be exceed by n square. So option B, as you can see here, option B is discard here directly. Now come to the question or solution. Or you can write dimension, and W is a subspace of M and R. Therefore, its dimension will be at most dimension of M and R. And its dimension is n square. So dimension, therefore, dimension of W never be infinity. You can generalize this point also. Hence, option B, discard here or eliminate. Discard here. Now call this as equation 1. By equation 1, possibility of dimension of W among from option A, option C, and from option D. Also, if n tends to infinity and none a raised to the power n is repeating, then, or repeating elements of spanning set, or elements of spanning set of W, then dimension of W might be infinite, but it is not possible. By equation 1. Let consider an element A is in vector space M and R. Then we can write care equation. How we write care equation? A minus lambda I, and its determinant, expansion of its determinant, will give you care equation. And we normally care equation C for care, A for matrix A, and if it is in variable x, then we use x. So care equation will have the structure x raised to the power n plus a naught x raised to the power n minus 1, and so on. an minus 1 x plus an. This is the format of Kerr equation or somehow. And by Cayley-Hamilton theorem, we know that matrix satisfy Kerr equation or any annihilating polynomial. But Cayley-Hamilton theorem is specified only for Kerr equation, but matrix satisfy any annihilating polynomial. By Cayley-Hamilton theorem, matrix A will annihilate Kerr equation that is a raised to the power n plus a naught raised to the power n minus 1 and so on. Identity matrix. This constant term is formed by identity matrix, and this one equal to, because this is in the format of matrix, so this is the matrix of correct size, and size of this matrix is n by n. This implies a raised to the power n can be written as transpose other term minus of all these terms. A naught, a raised to the power n minus 1 and so on, in or unit matrix. And this is linear combination of some elements of a spanning set. Spanning set. What is a spanning set? A spanning set was identity matrix A square and powers of integral power of positive integral power of A. So this is linear combination of some elements of a spanning set, and for this or by, as I already mentioned in first remark, dimension of polynomial is 1 exceed by remark 4. So it is basically very basic, or by this remark 4, dimension of this one will be, or number of, you can write in linear combination, number of elements in a spanning set, in linear combination number of elements of a spanning set are n. Therefore, dimension of W is at most n. At most n. So by this theoretical approach or sufficient explanation, we reached at the point A, dimension of W over R is at most n, equal to limit of this, then s equal to 1 by 4, s is half, s is 3 by 4, and s is 1. Now focus on this. Define s 1 minus 1 upon 2 square, 1 minus 1 upon 3 square, and so on up to 1 minus 1 upon n square. It means you can see inside the bracket a square minus b square formula or identity is forming, and this is nothing but a plus b within bracket a minus b. Use this identity as equal to limit n tends to infinity, and expand these brackets using this identity. It will become 1 plus 1 upon 2 and 1 minus 1 upon 2. This is first expansion, and again in product 1 plus 1 upon 3 and 1 minus 1 upon 3, this will go up to 1 plus 1 upon n and 1 minus 1 upon n. This will end here. It means as you are increasing n, then this is tends to which number we have to identify. Now this is limit n tends to infinity. This first bracket will be 3 upon 2 and this is 1 upon 2. Similarly, 4 upon 3 into 2 upon 3 and so on. Check this one. It will be n plus 1 divided by n, and in other bracket n minus 1 divided by n. Now focus first and third term. Its numerator is cancelled out by its denominator 3. Means numerator of first term is cancelled out by denominator of third term. I will not say term, means fraction. And denominator of this one, or you can say denominator of second one fraction, as you are seeing this one fraction is cancelled out by, after skipping one fraction, its numerator. Means denominator of second fraction is cancelled out by numerator after a fraction skipping. Numerator, skip this one and it will cancel out next one. Means first denominator is left, means 1 upon 2, and if you proceed this like that, means skip one fraction, that will cancel out denominator, and numerator of coming one will cancel out by previous skipping denominator. Means this one cancel out by this denominator, and its denominator is cancelled out by just before this fraction its numerator. Means in the last n plus 1 divided by this one will left. It means take n as a common, 1 upon 2, it will be n plus 1, or you can write this one equal to, limit is tending to infinity, 1 upon 2, 1 plus 1 upon n. As n tends to infinity, this 1 upon n will tend to 0. It means limit is half. So option B is right choice. Expression x raised to the power 2021 plus x raised to the power 2020 plus and so on up to x minus 1 equal to 0. Then all real roots are positive. Exactly one real root is positive. Exactly one real root is negative, and no real root is positive. So this problem is related to roots and how many roots, either and nature of the root. So problem is related to roots, either positive or negative, and how many existence. These are few terms related to this problem. So how to solve this problem? So Descartes' rule of sign change can tell us how many real roots or real positive or real negative root for this polynomial, because of, you can say this is a polynomial structure of the equation. So how many roots will exist according to Descartes rule, we can easily find out. So first
What is the discard rule of sign change? Tell us. It is a technique for getting information on the number of positive real roots of a polynomial. By using the transformation x to minus x, we can easily tell about how many negative rule of polynomial exist. So what is the geometrical meaning or geometrical interpretation of the root? Geometrical interpretation of the root tell us x-axis intercept, means at how many places x-axis intercept. These are the meaning, or this is the meaning of root existence. Also, a very commonly used theorem in a real analysis we study about root. This is IVT, or intermediate value theorem. This says if a function f is continuous on domain, continuous over domain, and function is also continuous inside the interval or inside the domain and in this interval, then there exists a C such that before this a condition on hypothesis is that if f of a and f of b, product of these two endpoints of the interval, if product of this is negative, then there exists a C between a and b such that fc is 0. What it's a geometric meaning. Suppose this is the graph of the function, means going negative to positive either in increasing way or in decreasing way. So if negative to positive or positive to negative, either in concave up or concave down, we can see there exists a C lies between a and b such that this C is the root of the polynomial. So this is the meaning, geometric meaning of intermediate value theorem. And this is a corollary normally known as Bolzano theorem about the roots. If f of a, f of b is less than 0, means at the end point of the interval, means the image of the endpoints of the interval is a negative product of the image, then there exists a real root. This is normally known as Bolzano theorem. And the second thing is about the image of the endpoints. The image of the continuous function over an interval is itself an interval. This is image of continuous function over an interval is again an interval, is again an interval. This is second corollary you can study here. So as you can see, at a and b, these are 2 points normally we use in intermediate value theorem. So because structure of the polynomial is like this: x raised to the power 2021, x raised to the power 2020, plus and so on up to x minus 1. This is the structure. So you can say this is the polynomial px, or you can say fx. So normally when we check what are real roots of the polynomial, so normally or sometimes we put 1 minus 1 and 0, because of these are very elementary points, and calculation over these points is very easy, so we can try to find or judge these are the root or not. So value of f0 will equal to minus 1, because of other terms minus 1 will go to 0. Value of f1 will be up to here, you can see positive value and minus 1. So means there are 2021 terms, so 2021 minus 1 will equal to 2020. So this is the value of f1, and value of f at minus 1 will be, you can see up to this, there are 20 terms, means 2020 terms. So one is positive and other is alternative positive and negative, so all will cancel out and remaining one will be these. So value of x minus 1 means after putting minus 1 will equal to minus 2. So value of f minus 1 is minus 2. So we have f0 is minus 1 means negative, and f1 is equal to 2020. So this is positive value. As I already told about geometric interpretation of the intermediate value theorem, one is positive and negative, so you can say f0 and f1 is negative. Product of these two is less than 0. So using by IVT or intermediate value theorem, we can say there exists a C lies between 0 and 1 such that Fc is 0. So existence of the root comes from IVT. But how many roots will exist? So it is at least, not at most. At least a C belongs in open interval 0 1 such that fc is equal to 0. But how many? The answer of this problem we can solve using Descartes rules of sign. As x raised to the power 2021 plus and so on up to x minus 1, there is only, because we are seeking over interval 0 to 1, so there is only positive real root. There is only positive real root because of only one sign change, positive to negative. So only one, and you can see 1 to infinity means over this interval or x greater than 1. So value of these terms will be positive, and how much? It will be 2021 minus 1. So entire value we will get a positive value. So means there is no point where fa fb is less than 0. So there is no real root in the interval 1 to infinity, means there is no existence of the root. And you can see minus infinity to 0, you can find how many real root exist. But you can see we have solved this problem. No real root is positive, but positive real root is existing by Descartes rule. So this option is false. All roots are positive. We will come on this option A. Before solving this, exactly one real root is positive. So this is true. Exactly one real root is negative. So solving this, exactly one real root is negative, apply Descartes rules. So we can see that after changing x or transformation x to minus x, we seen that up to x raised to the power 2021 and so on up to x raised to the power 3. Up to here, there are 20 terms. So one is negative, means alternate negative positive, and this is even. So half is positive and half is negative, so entire will cancel out. So value will depends on x minus 1, means after putting x to minus 1, so you can see value of this is negative, means there is no sign change because of after applying this transformation x to minus x. So minus x minus 1, so there is no sign change. So we can see that exactly no real root is negative. So this option is false. All means only and only one real root exists, and this is positive, means all real roots are positive. So option A is also true. The value of pi upon 2 limit cos pi by 4, cos pi upon 8, and so on up to cos pi upon 2 raised to the power n plus 1 is. To find the limit of this expression, we normally experienced whenever limit is asked for terms which are in product, then most of the terms cancel out and we have only some few terms. So this is given pi upon 2 limit n tends to infinity cos pi upon 4 into cos pi upon 8 and so on up to cos pi upon 2 raised to the power n plus 1. Normally we know the concept of limit whenever trigonometric function involve sine theta upon theta and theta is tending to 0. This limit is 1, and also when theta is tending to infinity, this limit is also 1. And for reciprocal also means theta upon sine theta, limit is same. So to find the limit, we are doing some manipulation. We are going to multiply by sine function limit n tends to infinity 2 sine pi upon 4. This is my first term, cos pi upon 4 divided by 2 sine pi upon 4. We need to divide this because we multiply in numerator. So this is my first term. Second term will be, I write second term, I write from starting point. N tends to infinity 2 sine pi upon 4 cos pi upon 4 and need to divide 2 sine pi upon 4. Next term will be 2 sine pi upon 8 and cos pi upon 8 and need to divide 2 sine pi upon 8 and so on. 2 sine pi upon 2 raised to the power n plus 1 cos pi upon 2 raised to the power n plus 1 divided by 2 sine pi upon 2 raised to the power n plus 1. In the numerator, we have 2 sine theta cos theta equal to sine 2 theta. So pi upon 2 limit n tends to infinity. Expression we have sine pi upon 2 and in denominator 2 sine pi upon 4. For second term, it will be sine pi upon 4 divided by 2 sine pi upon 8 and so on. Sine pi upon 2 raised to the power n, because this is 2 here, so you can write n plus 1 here, divided by 2 sine pi upon 2 raised to the power n plus 1. So 2 cancel out by this, so 2 raised to the power n. You can observe sine pi upon 4 cancel out by this one. This sine pi upon 8 will cancel out by next term. So we have only pi upon 2 limit n tends to infinity sine pi upon 2 and 2 left here, 2 left here, and this is also. So how many times? 2 raised to the power n times, 2 left, and the last term is sine pi upon 2 raised to the power n plus 1 we have. Now value of sine pi upon 2 is 1. So this is pi upon 2 limit n tends to infinity. This is 1 upon 2 raised to the power n sine pi upon 2 raised to the power n plus 1 we have. Now you can take this here. So this will be limit n tends to infinity pi upon 2 raised to the power n plus 1 into 1 upon sine pi upon 2 raised to the power n plus 1. So you can write this expression like this: pi upon 2 raised to the power n plus 1 in numerator divided by sine pi upon 2 raised to the power n plus 1. Finally, this will comes out below this friction line. So this is, you can consider theta, and this is sine theta, and theta is going to infinity, means limit is